I like to dedicate my videos to someone or something that's had a positive impact on my life because making videos is boring, and this allows me to have a little bit of fun. So this one is dedicated to the Personal Development Institute dojo, the best little dojo in the whole world, if you ask me. The only dojo I could practice. So specifically, this is for the Little Ninjas class and Professor Chris Sprague, who is their Sifu. Thanks for doing such a great job with our kids. And if you guys are ever in Waianae and want to have a really great program for your kids, check it out. Okay, we're going to try this one more time. My computer just shut down on me. Okay, this is going to be lectures 7 through 9, and I'm going to do the last part, measures of dispersion. Okay. Okay, remember back to measures of central tendency. That's just a single number used to describe a group of numbers. So on average, how do all the, what does the group of numbers look like? So like if I went into my daughter's kindergarten class and I could give you an average age, I would say, well, on average, the age of those kids is probably 4.5 years or 5.2 years or something like that. So it's a single number used to describe a whole bunch of numbers. A measure of dispersion is the same thing. All it does is it's a single number used to describe how spread out a group of numbers are from each other. Okay, so go back to my daughter's kindergarten class. Would you expect their age, if you took everyone's age, would you expect it to be closely grouped? Would it be spread out or would it be closely grouped? As compared to one of my classes, if you've never been to West Oahu, we have people anywhere from age 18 all the way to in their 60s. Okay, so if you were to take a West Oahu class in person, a college class, would you expect their ages to be closely grouped or spread out? Okay, so in kindergarten, we'd expect them to be closely grouped, right? We'd all expect kids in kindergarten to be between 4 and 5 years old. Okay, in college, we would expect all those numbers, the ages of everybody, to be more spread out from each other. So we're going to come up with numbers that tell us how spread out the data are. In general, if the number's small, the data is not very spread out. If the number is large, the data are more spread out. Okay, so let's start with, this is directly from the lecture over here. Okay, so the easiest thing to do is called the range. Okay, and that's the biggest number minus the smallest. So in this case, it's 7 minus 1. 7 is the largest number, so 7 minus 1 equals 6. So in this case, the range is 6. Okay? So that is quick and dirty. It's very easy to get. It is the only choice if you have a nominal or an ordinal variable. Okay? The only choice for a measure of dispersion. As you will see, the variance and the standard deviation are based upon the mean. And so the mean only makes sense when we have a interval or ratio level variable. Okay? You can compute the standard deviation of a nominal variable, but it's meaningless. Just like you can compute the mean of a nominal variable, but it's meaningless. Okay? So this is a data set where we've got 4 people. Okay, I'm just doing that so you can see there's 4 people. Okay, that will get you the n, if you will. Okay, and here's the actual data. I don't know what this represents. Okay, we could say it's how many dollars do you have in your pocket right now. Okay, so it's a ratio level variable. So that person had $1, $3, $5, $7. Okay, if you added those up, it would be 16. Okay, sum of x means add them all up. Okay, you would take the mean, which remember is the sum of x over n. Okay, so 16 divided by 1, 2, 3, 4 is 4. Okay, so what you see there is the mean. Okay, so where we're heading for is we're going to compare all of these data points to the mean. Okay, a measure of central tendency, something that should be in the middle. Okay. Now I just chose these numbers because they add up nicely, as you'll see later. Okay. So this column over here is just x minus the mean. So it's 1 minus 4, which is minus 3. Okay, for those of you who don't understand the number line, think it's your checkbook, minus $3. Okay, you got to understand the number line. Okay, but that's one way to do it. 3 minus 4 is minus 1. Okay, 5 minus 4 is 1. 7 minus 4 is 3. Okay, if you add those up, it equals to 0. So the sum of x minus mean, that little Greek thing just means add them all up. If you've seen Excel, that's the same thing. Okay, add them all up, it equals to 0. Okay, that's not very helpful because there's some dispersion, there's some spread outedness here, is there not? Okay, sorry, my computer's acting up again. Okay, so there is some spread outedness. So that 0 isn't helpful. So whenever you do this, if you have too much time in your hand, trust me, it'll always work out that way. So what we do in math is to get rid of the negatives, okay, one way to do that is to square them, times them by themselves. So minus 3 times minus 3 is a positive 9. Okay. Minus 1 squared is 1, 1 times 1 is 1, and 3 times 3 is also 9. So if you add those all up, which would be top part of this fraction, and I'm going to try to write it a little bit bigger here. So add those all up. That's 10 and that's 10. It's 20. Okay? That's the top of this fraction, is 20. Okay, so don't get freaked out when you see that. I'm giving the actual population formula, but right now we're starting with that for a reason, okay? So don't get freaked out. Okay, there's a sample formula that we'll deal with later, okay? So you add those all up, and then you divide by n. N would be the number, 1, 2, 3, 4. That's the variance. 20 divided by 4 is 5, okay? Okay, so on average, how much do all these data points differ from the mean? Okay, if you look at this formula, you have a sum sign and you have an x. That should look like this formula right here. That's the formula for the mean. Okay, sum of x over n. So you can play the Sesame Street game and you can see those look somewhat similar. You just substitute the x. Sorry, I don't know if this is working here. Substitutes the x. Okay. So it's a formula for the average. Okay, and it's saying on average how much do all these data points differ from the mean. Okay. Now, the problem with the variance is we squared these numbers to get rid of the negative sign. Okay, and the way that we undo a square is we use the square root. So if you take the square root of this, you now have the formula for the standard deviation. Okay, so if you take the square root of 5, it's 2.2 something, I forget. Okay, punch it into your calculator. That's the standard deviation. So the standard deviation to me makes more sense than the variance because it's truly the, on average, how much do all these data points differ from the mean. Okay, so we could say, because we've undid the square, okay, that's why you see standard deviation much more than variance, okay, because it makes more plain English sense. The variance is hard to tell you what it means in plain English. In fact, I come up with something that's not very satisfying. But the standard deviation is nothing more than, on average, how much do all these data points differ from the mean? If you get a big number, that means they differ from the mean a lot. If you get a small number, that means they don't differ so much. Okay? So, on average, these data points differ from the mean of 4 by about 2.2. Okay? That's all that means. That's the standard deviation.